next speaker, and I'm very pleased to welcome, or I would rather say welcome back, Kateryna Zorina, because Kateryna is our graduate of our master program in data science, but before she graduated from Kyiv Polytechnic University, and now she works on very cool things in the research group of Professor Josef Shivitz. And Kateryna, the floor is yours.
Thank you very much. I'll just set up. Okay, so today I will tell you about the paper that we presented at ICRA last year. And the main thing that we wanted to study in this paper is if you can use the demonstrational videos, instructional videos, to speed up. Oh, this is a bit too early. Oops. To speed up the planning. Okay, never mind. So the input to our approach is the video of human manipulating some objects. And from this video, we estimate the contact states between human and the object, and also the pose of the object. My presentation is sort of a compilation of videos. Maybe it's a bit weird. I will play them at least 2 times. But actually, we're good. From this information, we will construct, maybe I will just pause it here to talk a bit more about it. We will construct a space in which then the planner will search for the optimal solution. Well, as optimal as it can be with the sampling-based planners. Okay, sorry, let's go here. Yes. So here, as you can see, here is on the left, maybe I'll just move this slightly higher. It covers the screen a bit. Or lower, okay. So here on the left, you can see the example of the frame from the video that you saw earlier, and on the right, the recognized pose of the objects. And so this will initialize the first placement state, as we call them, for the planner. What we mean by placement state is the manifold where each point in the state would, state will be the robot joints together with the object poses. And we put the constraint that objects cannot move in the placement state. So they remain static on the environment surfaces. In this case, it's the table. And the robot can move, so the joint positions can change, but the objects remain static. I know, why are you doing that? So then in the video, after the first object is moved and the contact with the hand is done, we will initialize the new placement state after one object is moved. And also to get from one placement to another, we need to go through the grasp state. Here, as example, we show the 2 grasps on the top and on the side. But in general, you can define any amount of grasps for your object. It's basically just a transformation between the robot gripper and your object. And finally, after moving the second object, we initialize the final placement state at P3, and also again 2 grasps. So this is just an example sequence of state that we initialize. So in theory, there can be more of them, but just to go a bit more about them. So again, we start with the 2 object poses, and then we will create a sequence when first just one object is moved and then the second object is moved. And to get from one state to another, you need to go through the grasp, where the constraints in the grasp state will be that the object is fixed with respect to the robot gripper. So for example, like this configuration will be the grasp configuration. And to move from the placement to grasp, you will go through this like border states, where basically the robot is approaching the object. And then there is a heuristic which allows it to, oh, sorry, I'm a bit nervous, which allows to go down, grasp the object, and now we're in a grasp state. And obviously, if you have more than 6 degrees of freedom in your robot arm, there are multiple ways to grasp this object. And also if you have several handles, like on the top or on the side, there are multiple ways. for this for multiple grasp states. And finally, yeah. And finally, we perform a search in this space, also spanning the additional trees. It's RRT-like search, and we span additional trees in this intersection of the states to explore more efficiently all the different grasps and all the different placements. And here you can see the visualization of the final path that was found by the planner executed on the real robot. So here it shows the grasp G1 and grasp G4. Yeah, every dot is our configuration. So the robot joins together with the object poses. And the green dot represents the end goal. Okay. We test our methods on 3 tasks. One is the shelf tasks, where you need to move several objects from one surface to another. Then there is a tunnel task, where one object needs to be passed through a narrow tunnel and taken by the robot from the other side. And finally, the waiter task, where several objects need to be placed on the tray and transferred to another position, similar to the way the waiter will do it. Maybe quickly some results. So we compared to the one of the baseline methods was the humanoid path planner, which is basically like the backbone of what we work with. They have the same definition of placement and grasp states, but they don't guide it by the video, so they will search without any knowledge of. Basically, they don't restrict what placement states you can use, so they will search a much larger space in order to arrive from the beginning, like start configuration, to the goal. And we compare to the PDDL stream, which is a symbolic planner that uses the sampling methods just as black boxes. So it will find a symbol plan and then try to use the samplers to find like every piece of the, for example, grasps and stuff like that, and plan between the configurations. And just to highlight a few, so for the simple task where you need to move one object, all of the methods are quite successful. For a PDDL stream, its success rate is a bit lower because it is more random. So if it gets stuck on the sampling stage, it will not produce a valid result, and we are more consistent. But still, for example, the basic HPP is having even more stable success rate. But as soon as we go to the tasks with more objects, so bigger search space, the baseline HPP method is failing to find any solution, and PDDL still finds quite a valid solution just with a lower success rate. And interestingly, for the task where there is a narrow passage which needs to be discovered, only our method is able to solve it, since we provide the guidance. So we say that you need to visit this pose inside the tunnel, and then this allows us to find the solution. I think here I have some examples. No, okay. Yeah, here I have just the final part. So one of the critiques of this method when we presented it on the conference was that, so okay, you can find the way to solve this particular task, but if you move the objects just slightly, it will fail, since it sort of assumes, after the execution is started, assumes that objects are, even we just take one demonstration and we assume that the objects are not moved in the execution phase. So after the conference, we also started the way to generalize this method and how can we approach it. And here you can see some modes of generalization where we change the objects or change the object pose or change the furniture pose. And here are the results that we are able to achieve. Having just one demonstration, we can adapt from it to new different setups. And we also tested it in the real lab. So if in initial setup, we assume that both goal objects and start objects, object poses are given by the instructional video. Here we assume that, okay, only the goal poses are given by the video. The start poses need to be scanned before we start the execution. So here on the left, you can see the scanning procedure, which gives us the current object poses. And then we replace the initial placement state and replan. And this is the execution of the final plan. And on this, I will conclude. And I'm ready for the questions.
Thank you so much, Kateryna. Are there any? Oh, let's thank Kateryna for a very interesting presentation. Are there any questions? Yes.
Thank you for presentation. We're just interested in how did you test your approach? Did you use any type of simulator here, or was it in a physical environment?
For these numbers, so for this table, we did everything in simulation. So most of the evaluation was in simulation. And the real experiments that I was showing were more to validate that it will actually work in the real life. But basically here we sort of assume that the objects are at the exact same pose as during the demonstration. So it will work if they remain there. But and yeah, again, in the generalization setup, we only tested it like a few times to see that it actually adapts to different object poses, but we didn't include the numbers into. So okay, when I say simulation, it's basically just the geometrical simulation in the sense of we have the scene and we have the planner. It's not physical simulator. When I say simulator, I basically mean that like the planning environment. And we assume that objects are nice and rigid, and if we grab them, they remain exactly as they placed. So one of the problems, for example, that we face that if you define handles poorly, and then in your simulation, you sort of assume everything is nice and geometrical and there is transformation that is static. But then if you define handle like this, the simulator would assume that you would pick it up and it will be like this. But what happens is, but then simulator, the planner still thinks that it's like this. And then when it tries to put it, it's like crashes. But yeah, here we assume that everything is perfectly geometrical.
Thank you. Any other questions? I have one more question. In some of the experiments, the robot was moving. It could change, relocate. Yes. In some, it was fixed on the table. Yes. Yeah. So my question is, can we somehow combine these two, for instance, to allow the fixed robot to first slightly move the objects to a preferable position and to simplify the task?
You mean like to have the mobile robot that would slightly adjust the position of the object before grasping it, or?
Fixed and slightly change the object first.
Yeah, that's an interesting question. I think mostly roboticists sort of avoid everything where there's something sliding or something like being just like pushed, mostly because it's that's what we do as humans, but it's kind of hard to predict how it's gonna. Yeah, it's a bit harder to predict. But I would say, for example, as if you do something like this generalization approach that I showed, where you, for example, you want some perfect location and you apply some motion for the robot to reach that location through pushing. I can imagine it being done. I never worked on it. I sort of assume we don't push stuff, we just grasp stuff. But sounds reasonable. I haven't seen works on this topic yet, but I think some people do it in more like tabletop manipulation. So they would like arrange the objects through pushing, but slightly harder.
Thank you. Any other questions? If not, then let's thank Kateryna and all the speakers of this session for very, very insightful presentations. Thank you so much.